Hi, welcome to the last part of the tutorial on an introduction to multivariate calculus. Let's now go through a short introduction to integrals in high dimensions, as well as some abused notation which is used quite informally. And you'll come across it in your lectures as well as in books and papers and talks and so on. And it's good to know what they mean when they write something. So let's go through that. Now, for multivariate integrals, to integrate f of x, where x is actually a vector like x1 comma x2 over a domain D, we actually should write something like this. So we should write integral over of x1 and x2 belonging to D of f of x1 x2 dx1 dx2, or maybe sometimes d of x1 x2. Right? So sometimes we might write something like that, and this is the full expanded notation. But sometimes people might just write integral over d f of x dx. So here x is understood to be a vector and d is understood to be the domain for that vector. And sometimes people just write integral f when the domain of f is understood, and when it's understood that you're integrating over the variable x and so on, then people might just write integral f. In fact, this is commonly used when the integral is actually over the entire reals, say something like it's over Rd or something like that. Then people just sometimes write integral f. So they might say that integral p is 1 for all probability distributions. And so that actually really means even higher dimensional probability distributions over the entire domain on which those distributions are defined. Right? So you shouldn't get confused when you see notation like that. They really mean something as elaborate as that, but because it probably gets too tedious to write this entire thing out every time, sometimes people just write that informally. As long as both people know what they mean, everything's fine. Remember that D need not be a rectangular domain. So for example, D could be the circle x1 square plus x2 square is equal to 1, right? And f of x1, x2 need not be separable, in the sense that it need not be separable into a product of a function of x1 and a function of x2, or a sum of two such functions which separates out those variables. It could very much be something like sine of x1, x2, right, or something of that sort. Now, that complicates things. Integrals are not always easy to calculate. But if we are in the case that we are in a product domain, that is D is a rectangular set, which is D1 cross D2, which basically means that X1's domain is D1 and X2's domain is D2. And if f of x1, x2 actually was f1 of x1 times f2 of x2, so it decomposed over the variables, then the integral over d f of x dx is basically, it can be written as the integral over d1 of f1 of x1 times the integral over d2 of f2 of x2. Or maybe a more succinct way that you might see that is integral over df is integral over d1 f1 times integral over d2 f2, right? And so this would then reduce to one-dimensional integrals. Here are some more properties about multivariate integrals. There are some conditions under which this theorem holds. For example, it's called integrability of f, but let's just ignore that for the moment. But one of the standard things that people do is to evaluate integrals one at a time. So suppose I'm evaluating the integral of f over a domain x cross y, then actually what I can instead do is evaluate the integral over just y first, with respect to y first. This will give me some function of x, and then I evaluate the integral with respect to x. And this theorem says that this actually gives the same quantity. I can also do it the other way around, where I can evaluate the integral with respect to x first, and that will give me some function of y, and then I integrate that with respect to y. And a particular Fubini's theorem says that all of these three are actually equal. And so you can choose your own order of integration, as there is a condition of integrability, but let's just say for now that you can choose which order you want to integrate in. And one example of that is that the volume of a cuboid is, say, the integral from a to b, c to d, and e to f of 1 dx dy dz, which would just be b minus a times d minus c times f minus e, no matter what order you integrated x, y, or z in. You could integrate them in any order, and it would still end up giving something like this. I mean, it would end up giving exactly this. Another important thing to keep in mind is integration by parts. This, of course, holds even in high dimensions. So if I have f of x times g prime of x dx, then I can write that as f of x g of x minus g of x times f prime of x dx, taking the integral. Now, more succinctly, integral f dg is fg minus integral g df. Now, this notation might seem a little confusing at first, but if x is high dimensional, then what this is basically doing, f of x is a scalar, so that's fine. G prime of x is actually a vector. Dx is actually a vector. And this actually means implicitly that we're taking the transpose. So sometimes it will be explicitly written in with the transposes in the right places because we are dealing with vectors. But sometimes if this something like this is said, then it's understood that if this was in high dimensions, then this term is actually supposed to mean the gradient of f at x. That's the notation used for the gradient sometimes. Transpose dx. Right? So it's a little more complicated in that setting. Let's look at some important integrals, some examples which you will come across quite often actually. One's called the Gaussian integral. In one dimension, it basically says that if I integrate e to the minus x squared from minus infinity to infinity, then I get root pi. And this you can think of as a one-dimensional integral. The same thing in high dimensions would be written something like minus infinity to infinity e to the minus norm of x squared dx, right? Now, I can split the norm of x squared. If you remember that the norm of x squared from our previous lectures was basically x dot x, which basically is the sum of xi squared for I is equal to 1 to d. So you can write this out, this term out as a summation. And you know that exponents of a summation is the product of the exponents. So what this integral would mean actually is integral of each of those variables from minus infinity to infinity. I can write that succinctly as integral over rd, right? But if I'm writing down d such integrals of e to the minus norm of x squared, again this dx really means dx1 to dxd, okay? And then I can actually, because I can write this out as a product that splits, we saw earlier that if I can write my function as in a separable form and my domains are all separable, it's a product domain, it's a rectangular domain, then this just splits up into the product of the individual integrals. So this just actually ends up being the integral of minus infinity to infinity e to the minus x squared dx, and that gets multiplied d times, so it's to the power d, and so that just ends up being root pi whole to the power d. So that's the higher dimensional version of the Gaussian integral. Another important integral is the Fourier transform. In one dimension, that looks like the Fourier transform of f of x is f hat of t, which is integral from minus infinity to infinity f of x e to the minus 2 pi I x t dx. Here, remember the e to the I 2 pi, if you remember that I is the square root of minus 1, then such a function is basically sine of 2 pi xt plus I cosine of 2 pi xt. Again, you should know this from your undergraduate math itself. And when I integrate this with respect to x, I get a function of t, and that function of t is my is the Fourier transform of f of x. If you are not familiar with the Fourier transform, hopefully you'll learn about it in other courses. Another important example is that the expectations of functions of random variables are integrals. So you'll often see people writing expected value of f of x where x is distributed according to p, and okay, so somehow not able to write p, but just imagine a p written over there, so that the x is distributed according to p. And when I write expected value of f of x, that basically stands for an integral, and we shall see that later on in the probability section of the tutorials. Another important case of integration is in statistics is the moment generating function, which turns out to be the Fourier transform of distributions. And again, hopefully you shall see that in other more intermediate statistics courses or other statistics courses. And I just wanted to give you that, integrals do appear, multivariate integrals do appear quite consistently in machine learning and statistics, because we are always looking at expectations and moments of different functions of random variables. So that's all we have for the moment for multivariate calculus, and there should be a set of tutorials coming out soon on multivariate probability and understanding probability distributions and just the basics at least of probability, and a lot of this will get applied over there.